Hello there. Thanks for tuning into my video. I'm Jake, and today I'm going to be talking about computational chemistry once again. Specifically, I'm going to be talking about how to calculate pKa and oxidation potential for various chemical systems using density functional theory, and then using that data to computationally construct a Pourbaix diagram. So as a forewarning, pKa and oxidation potential calculations are not going to be the most accurate. You can usually get pKa values within around 1 unit of your experimental value and oxidation potentials within roughly 200 millivolts of your experimental value. So don't expect it to be the most accurate, but it can be useful for affirming whatever predictions you have about your chemical system. Also, the basis and functionality that you use is going to drastically change your results. So make sure when you're doing these calculations to do some research on what the best functional and basis to use will be. And in the future, I plan on uploading a video on how to choose the correct basis and functional. So if you want more information on that, subscribe and check out the video that I have in the future. Today I'm going to be using Chem and IQmol to do these calculations, but the methods that I use should be applicable to whatever computational software you're using. So whatever I'm doing, just translate it to your computational chemistry software, and you should be able to replicate my results. So for calculating pKa, you're going to want to construct your protonated and unprotonated form of your chemical system. In my previous video, I talked about building molecules and how to construct them in the right form, so consult that video if you need help with that. And then once you have your built molecules, you want to perform optimization and frequency calculations. Again, I talked about that in the previous video, so if you need help with that, check out those ones. And then once you have your optimization and frequency calculations completed, you'll be able to determine the total energy of both your protonated and unprotonated form of your system, and use this equation to do that, where the total energy is the summation of your electronic energy and Gibbs free energy of each system. So for these calculations, you'll also need the standardized total energy for a solvated proton. And at the bottom here, I have a good reference for determining what that energy should be. And if you look at that reference, which was published by the Custodio group in the Journal of Physical Chemistry in 2021, you'll find that they did a DFT study on 22 different acids and used those calculations to empirically determine what the best energy value for the solvated proton should be. And if you scroll down in the paper here and look at this table, you can see that for a range of functionals, they give the best energy, best empirical value for the energy of the solvated proton, and this is listed in kcals per mole. So today I'm going to be giving an example using the functional MO62X. So for that calculation, we'll want to use this value for the energy of the solvated proton, negative 273.14 kcals per mole. And this was achieved using their training set 1, which is from the complete study of 22 different acids. So we'll use this value to calculate our delta E values. And to calculate delta E, we'll use this equation here, where the total energy of the protonated form of your species will be used, and you'll subtract the total energy of the unprotonated form and the energy of the solvated proton. So once you have your delta E value, you'll be able to use the Nernst equation to find K. And I've rearranged the Nernst equation so that we can have K in terms of the delta E value. And then using the standard convention for pKa, we can use this K value to determine the pKa. So the pKa will be calculated using the delta E divided by RT ln 10. And if you're wondering where this ln 10 value comes from, It's basically a rearrangement of logarithms. You take a log of an E value, and that'll give you ln10. So once you have the energy for your protonated species, your unprotonated species, and the solvated proton, you'll be able to calculate pKa. And today I'll be giving an example with acetic acid, and we'll be calculating the pKa of acetic acid. So here we are in our computational chemistry software. Again, I'm going to be using IQmol and QChem. You can replicate what I'm doing in whatever software you're using, and you should be able to get the same results. So to start off, we'll want to build our acetic acid molecule. So, as you're probably aware, acetic acid has a methyl group and a carboxylic acid group. So we can go ahead and build our molecule like this. And we now have a acetic acid molecule. And we'll now want to optimize the geometry and perform a frequency calculation. So in IQmol, we're able to do this by going up to Calculation, pressing QChem Setup, and selecting our options in the GUI. So again, to start, we'll want to do a geometry optimization. We'll use the method MO62X. And then today we're going to be using the basis OG CC PVDZ. You want to make sure the charge and multiplicity is correct, and here it is, correct for acetic acid. And one important thing to do for pKa calculations is add a solvation model, because it's going to drastically affect the energy of whatever ionic species you're calculating. So definitely want to add a solvation model, and in this calculation we'll go ahead and use SMD with water as a solvent. And now our calculation should be totally set up. We can use this as our input file and run the geometry optimization calculation. I won't show how this is done, but check out my previous video if you're interested in how to send a calculation to the server and run it. And then once we have our acetic acid molecule, we'll also want to make the acetate molecule. So pretty simple. Remove this proton, and the calculation is going to be exactly the same, except we want to make sure the charge is correct. So acetate is going to be a -1 charge, and the multiplicity is going to be a 1. So this would be a correct input file for the geometry optimization of acetate. So once both of these calculations are finished, I'll come back and then we can set up our frequency calculation. Okay, so we have our optimized geometry for acetic acid and acetate. These calculations will give us the electronic energy, but we still need the Gibbs free energy, so we'll need to perform our frequency calculations to get the enthalpy and entropy. To do that, it's pretty simple. We'll just change our optimization to a frequency. We can either do this by typing directly in the input or changing the calculate drop-down menu to frequency, and we'll now get a frequency calculation for the acetate and acetic acid. So I'll come back once both of these calculations are finished, and then we can look at our output files and do the calculations to determine the pKa for acetic acid. Alright, so both of our frequency calculations are finished for acetate and acetic acid. We can check this by going into our output file, scrolling to the bottom, and seeing, thank you very much for using QChem, have a nice day. That means our calculation was performed successfully. And we have our enthalpy and entropy values here at the bottom of the output. So now we'll want to do the calculation. So I've got an Excel sheet all set up for us to do our pKa calculation. And as you can see, we have values listed for temperature, 298 Kelvin, unless you make some changes to the calculation. We also have R in kcals per mole, which is 0.001987 kcals per Kelvin times mole. And we have the energy for our solvated proton, negative 273.14 kcals per mole. We also have places to input our electronic energy, our enthalpy, and entropy. And then I have conversions to go from the energy that we input in Hartrees to kcals per mole. And I also have a conversion for the entropy to go from calories per mole Kelvin to kcals per mole Kelvin, so that we have consistent units for all three pieces of energetic information. And then we have our total energy for the species, which is done again by adding the electronic energy and enthalpy and subtracting the entropy times the temperature. So we have this for both acetic acid and acetate. So we can go into our output files to find these values, and then we'll be able to calculate the delta E. So let's start with acetic acid. Looking at the output file, we can do a Control F for total energy and find that it's negative 229.04 kcals per mole, or Hartrees rather. And we'll also want to go into the output file for entropy and enthalpy, which is usually at the bottom of the file. The enthalpy is 42.02 kcals per mole, and the entropy is 68.5 calories per mole Kelvin. So we can paste that into our Excel sheet, and we now have the total energy for acetic acid, and we'll do the same for acetate. So we'll want to look at the frequency file. Again, search for total energy, which turned out to be negative 228.58 Hartree. And the entropy and enthalpy. The enthalpy was 33.159 kcals per mole, and the entropy was 63.8 calories per mole Kelvin. So we have total energy for both our acetic acid and acetate, and we can then find delta G by subtracting the protonated form from the unprotonated form and the proton. So here you can see delta G is J8, which is our acetate, plus B4, which is the solvated proton, minus the acetic acid. So you have a conversion of the unprotonated plus the proton and the protonated form. So we now have our delta G value, which was 8 kcals per mole, and then we can from there calculate the pKa, which takes the delta G and divides the temperature, the R value, and ln10. Again, from the slides, we have this equation. pKa is equal to delta E divided by RT ln10, and this gives us a pKa value of 6. So not exactly what the literature shows of a value of 4.8, but it's roughly 1 pKa unit different, and for most applications it's going to be close enough. It's not conclusive in all circumstances, and you're just going to have to live with that. Maybe you'll need to use a bigger basis set or a better functional, and perhaps you won't be able to use computational chemistry at all, depending on how close your values are. But in most applications, it's going to be good enough. So we got a pKa of 6, and that's what you need to do for pKa calculations. So now moving on to the calculation of oxidation potentials. We'll want to do the same thing as we did in pKa. We'll build our molecule in one of the oxidation states and optimize the molecule in that oxidation state. We'll then change the oxidation state of the molecule to whatever we predict it's going to be. And we'll then optimize it in the new oxidation state. You don't want to use the same geometry, because the oxidation state of your molecule is going to change how the geometry is optimized. So you want to optimize it in both oxidation states. And then once you have the optimized geometry for both oxidation states, you can perform a frequency calculation on both of those molecules. And from there, again, calculate the total energy using the electronic energy and the Gibbs free energy. And this time, instead of using kcals per mole, we're going to want to calculate our total energy in terms of electron volts. So here I have a conversion factor of Hartree's to electron volts. And then we can use this oxidation potential equation, which is from this paper. So if you look at this paper published in Angew in 2012 by the Truhlar group, you can scroll down and find the equation that they used to determine the oxidation potential. And one thing I found from using this equation is that in the units they give of electron volts, you actually don't need this Faraday's constant. This is something that I am going to talk about in my soon-to-be submitted paper. So if you're using units of electron volts, just make sure you use this equation without Faraday's constant. So if we look at this equation a little bit deeper, we can see that our oxidation potential is determined by the energy of the oxidized form of the species, the energy of the reduced form of the species, the number of protons times the energy of the proton, and the number of electrons times the energy of the electron. This all gets divided by the number of electrons transferred and standardized to the normalized hydrogen electrode. Some things that make this equation a little bit easier are the definition of the electron, which tells us that the energy of the electron is 0 electron volts, and the number of protons transferred in an oxidation reaction is going to be 0. We can also see from the literature that this value for the normalized hydrogen electrode is 4.28 volts. So we can simplify this equation to only include the energy of the oxidized form of the species, the energy of the reduced form of the species, and the number of electrons. So using this equation here, we can calculate the oxidation potential of a chemical reaction. So I'm going to give an example using a species from my research, where we start from a ruthenium-2 species and oxidize it by 2 electrons to get a ruthenium-4 species. That's a +2 charge. So I'll talk about how we do that. So back in our computational chemistry software, I have both the ruthenium-2 aqueous species and the ruthenium-4 aqueous species. So again, we're going to want to perform a geometry optimization and frequency calculation for these species. The ruthenium-2 is a neutral compound, so it has a charge of 0, and the multiplicity is 1. And use whatever basis and functional you're planning on using. And then we also have the ruthenium, which is the calculations are performed in the same way. We do a calculation of the geometry optimization and the frequency, but this time the charge is going to be +2. And interestingly, we found that the energy was lower in the high spin state with a multiplicity of 3. So if you're calculating a molecule that has the opportunity to be in either a low or high spin state, you're going to want to calculate the multiplicity in both states and determine whichever energy is lower. So here we found the multiplicity 3 state is lower in energy than the multiplicity 1. So this is going to be the calculation we perform. And once these calculations are done, we'll again have the enthalpy, entropy, and electronic energy, and we'll be able to calculate the oxidation potential. So again, I have a spreadsheet set up to perform this calculation pretty easily. In this one, we'll need to make sure we know the number of electrons transferred. So going from ruthenium-2 to ruthenium-4 is a 2 electron transfer. we also have the energy for the normalized hydrogen electrode here. Not the energy, but the potential. And again, we have places for the electronic energy, enthalpy, and entropy. And this time, instead of using kcals per mole, they get converted to electron volts. So from Hartree, we can convert the electronic energy to electron volts by the conversion factor of 27.2114. And the same thing, or similar, for the entropy and enthalpy. We convert kcals per mole to electron volts by the conversion factor 0.043363. And this time, the entropy is also going from kcals per mole. So it gets converted first from calories per mole Kelvin to kcals per mole Kelvin, and then that gets converted to electron volts. So then we can calculate the total energy of each chemical, each compound, by using these values in electron volts, total electronic energy, enthalpy, and entropy. So electronic energy plus enthalpy minus the entropy times the temperature. And again, the temperature is 298 Kelvin. So we can go ahead and look at our output files. I'll look at the ruthenium-2 aqueous species first. The frequency has an enthalpy of 328, put 292 kcals per mole. So we can paste that in, and it gets converted to electron volts. And we look at the entropy, 229.796 calories per mole Kelvin, which gets converted to electron volts per Kelvin. And I also have a single point energy calculation to have a more accurate electronic energy. So if we search for total energy, we get a value of negative 2,206 Hartrees. So that gets converted to electron volts. And we get a total electron volt energy of negative 60,025. And then we'll do the same thing for our ruthenium-4 species. We can look at the output for our triplet ruthenium-4 aqueous species. First, for the thermodynamics, we have an enthalpy of 326.690 kcals per mole. We have a entropy of 223.098 calories per mole Kelvin. And if we go into our single point energy calculation, we can find that we have a total energy of negative 2,205 Hartrees. So we have total energy for both species in electron volts. We can then find the delta G by subtracting the total energy of each species. So here I have the ruthenium-2 aqueous species subtracted from the ruthenium-4 aqueous species. And this gives us a delta G value of 11.4 electron volts. And then from here, we can use the equation from our PowerPoint. The oxidation potential is the oxidized energy minus the reduced energy divided by the number of electrons minus 4.28 volts for the normalized hydrogen electrode. So here we have the delta G, which is oxidized minus reduced, divided by the number of electrons, which is 2, and subtract 4.28 volts, and this gives us an oxidation potential of 1.429 volts. And I don't have a way of showing you that this is correct, but once we start talking about the Pourbaix diagram, I'll have more evidence that this is the correct potential. And for the construction of Pourbaix diagrams, you'll probably want to have an experimental Pourbaix diagram to better predict what each transition will be. If you're unfamiliar with Pourbaix diagrams, it's a plot of pH and potential, and based on the slope of these diagrams, you're able to predict how many protons and electrons are transferred. So the slope of a Pourbaix diagram will be relevant to the number of protons divided by the number of electrons, and this gets multiplied by 59 millivolts. So if you have a 1 proton, 1 electron transfer, your slope is going to be 59 millivolts. If you have a 1 proton, 2 electron transfer, it's going to be half of that at around 30 millivolts. So as you can see from this Pourbaix diagram on the left, going from water to O2, you have 4 electron, 4 proton transfer. So this is going to be a ratio of 1, and you get a slope of 59 millivolts. And from H2 to H2O, you have 2 proton, 2 electrons. Once again, the ratio is going to be 1, and you have a slope of negative 59 millivolts. The experimental Pourbaix diagram for our ruthenium species had a slope of 32 millivolts, so this tells us that we're likely having a 1 proton, 2 electron transfer, which is why we predicted a transformation from the ruthenium 2 species, ruthenium 2 aquo species, to the ruthenium 4 hydroxo species. However, the calculation of a direct proton-coupled electron transfer is not simple. Usually can't get accurate values, especially because this calculation or this transformation is dependent on pH. So in order to calculate this Pourbaix diagram, we can extrapolate our data to the edges of these transformations. So I have an example of this extrapolated Pourbaix diagram. We imagine that this sloped proton-coupled electron transfer region finishes, and we get a region where there's a simple electron transfer at both ends of the regime and an associated proton transfer. So here, at the end of this regime, we predict that the ruthenium 2 aquo species has an oxidation to the ruthenium 4 aquo species. So that's a simple electron transfer reaction, which is what we just talked about in our calculation of oxidation potential. And similarly, at the most basic region, we have an oxidation from the ruthenium 2 hydroxo species to the ruthenium 4 hydroxo species. And in between both of these regions, there's going to be a proton transfer reaction. And at the intercept of these points that I have circled in red here, these are going to be the points we're trying to identify using 4 reactions, the 2 oxidation reactions and the 2 proton transfer reactions. So it's important that we know how to do the pKa and oxidation potential calculations so that we can construct our Pourbaix diagram. And as you can see here, I've got a sample of our proton transfer reactions from ruthenium 2 hydroxo to ruthenium 2 aquo. So this is going to be one proton transfer reaction that we calculate. We have the other one here at the top from ruthenium 4 hydroxo to ruthenium 4 aquo. And then we have the 2 oxidation reactions from ruthenium 2 hydroxo to ruthenium 4 hydroxo and ruthenium 2 aquo to ruthenium 4 aquo. So we do these the same way as I talked about before, where you calculate the oxidation potential and pKa, and then we'll be able to plot these points on a graph so that we can computationally construct our Pourbaix diagram. So once again, I have a spreadsheet set up so that we can construct this Pourbaix diagram. And here we're going to be incorporating all the knowledge we gained about performing pKa and oxidation potential calculations and combining them into a single graph. So in this template, I have all of the things we noted before: the temperature, the value for the potential value for the normalized hydrogen electrode. We have R, we have the number of electrons transferred, and we have the energy for the solvated proton. And as before, we have the values of the electronic energy, the enthalpy, and the entropy, converted to both kcal per mole and electron volts, which allows us to have the total energy in both kcals per mole and electron volts. And from our previous calculations, we have the energy for our ruthenium-2 aqueous species and the ruthenium-4 aqueous species. So we only need to add our energy for the hydroxo species. And just like before, we have calculation of the potential between the ruthenium-2 aquo and the ruthenium-4 aquo, and the potential between the ruthenium-2 hydroxo and ruthenium-4 hydroxo. So this is calculated just like we did in before. The pKa's are calculated just like before, from the ruthenium-2 aquo to the ruthenium-2 hydroxo, and from the ruthenium-4 aquo to the ruthenium-4 hydroxo. So if we look at our diagram, we have now calculations for both pKa and the oxidation. And then we just bring these values into a graph where pKa and potential are related, so that we can find the two endpoints on our Pourbaix diagram. And all we need to do is input our energy for our other species, and we should be able to get an accurate Pourbaix diagram. So if we look at the energy for our ruthenium-2 hydroxo species, first we'll look at the thermodynamics. The enthalpy has a value of 319 kcals per mole. So we'll go ahead and paste that in. Look at the entropy, 226 calories per mole Kelvin. And we want to look at the single point energy calculations for the total energy, which is negative 2,205 Hartrees. And we'll do the same for our ruthenium-4 hydroxo species. So we look at first the thermodynamics, enthalpy of 320 kcals per mole, and enthalpy of 230 calories per mole Kelvin. And the electronic energy of 2,205 Hartrees. So we have total energy in terms of kcals per mole, which is used to calculate the pKa. We have total energy in terms of electron volts to calculate our potential. And then these points are plotted on the graph, where the low pKa is associated with the high potential, and the high pKa is associated with the low potential. And we can see this red line is our computational Pourbaix line, where a proton-coupled electron transfer reaction is occurring. And if we look at the slope of this graph, we can see that our slope is very similar to what we obtained experimentally. The potential is off by about 200 millivolts. So depending on the type of calculation you're trying to do, may not be accurate enough. But for our case, it seems to be close enough to confirm that these are the correct states for our predicted transitions on the Pourbaix diagram. So that's about it. We've got our computational Pourbaix diagram that gives us a slope of 29.6 millivolts, where each state corresponds to our predicted states, where each state corresponds to the predicted states of the system. So that should be it for the computational construction of Pourbaix diagrams. Hopefully you're now able to calculate pKa, oxidation potential, and construct these Pourbaix diagrams using computational chemistry. If you have any questions, feel free to leave them in the comments or a private message, and I'll be happy to answer any of them. And yeah, hopefully this helped. Thanks again for watching my video. stay tuned for future videos on computational chemistry and maybe some other types of chemistry. And if you have any questions or want me to cover another topic, feel free to leave them in the comments. And thank you very much for watching. I'll see you next time.